So today's topic is multiple integrals. So this is integration of functions of several variables. So let's begin. The first part of this section is the double integral. First part is the double integral. Now, what is the basic definition of a double integral? Suppose we have a double integral of a function of x and y integrated over an area A. Now, this will be equal to summation of f xr yr on a fragmental area, applying limits r equal to 1 to n and limit n tending to infinity and delta a tending to 0. So there's the formal definition of a double integral. So we know the function of several variables. It's a three-dimensional problem. So this is the origin. And now function of several variables forms a surface. Say a surface like this, let us say this this is a surface. Now this is x-axis, this is the positive y-axis, this is the positive z-axis, this is negative x, negative y, negative z. Now this is the x y plane, z equal to 0. Now when we want to integrate the double integral, this is integral delta area. So suppose we divide this area of integration, let's say this is the area of integration, and we divide, let's say this is the area of integration, and this we divide into a number of parts, small infinitesimal parts. And this is the area under consideration, delta A. Now, corresponding to this, there will be some function values here on the curve. Corresponding to this point here. there will be this function values. I will mark in this color. Are you seeing this? So this is the XY plane. This area is this delta AR. Now within this will be a very small infinitesimal area. Although we are showing this big, actually it will be just surrounding a point. That's all. Now this area corresponding to that, there will be a coordinate XR, YR. So the function value of that multiplied by that area. So this gives us the volume. This gives us the volume of this. So we approximate it to a parallelepiped. So we get the volume of a parallelepiped, or this volume of this area enclosed within this. Now, when we do over an entire area, then we get volume bound by the surface and the surface over a particular area. So when you take a projection, you will get the full volume. So double integral gives us the volume. This is the double integral. The double integral represents the volume bound by the surface z is equal to f of x comma y and its projection over on the xy plane. So this is a volume generated. So double integral gives us the volume. So now how to, this is the geometrical interpretation of the double integral. Now how to evaluation of double integrals. Evaluation of double integrals, working rule. All right. So first one, when y1 and y2 are functions of x and x1 and x2 are constants, then f of x comma y is first integrated with respect to y, keeping x constant or treating x as constant. Then the treating x constant, then the resulting integral is again integrated with respect to x. So let us look at this scenario. You have double integral. This is y1 is a function of x and y2 is a function of x. x1 and x2 are constants, and we have integral f of x comma y dy dx. So this, the way it is integrated is, first we integrate with respect to y, because the limits of y are in terms of x. And then this is integrated with respect to x. So this is the working rule if x is constant and y is a function of x. Now, how will be the region of integration on the xy plane, the domain plane? Let us see the region of integration on the xy plane. So xy is the domain plane. So area, how will this look? So y is a function of x. So let's say y is a curve like this, and y1 is a curve like this, y2 is a curve like this. So this is y equal to y1 is equal to f1x, and this is y2 is equal to f2x. Now, the region of integration is x1 to x2. So what we are doing is, first step, we are taking integrating with respect to y. That means we are integrating from y1 to y2. So when we are integrating from y1 to y2, it means that we are taking a strip like this. A proper strip. Okay, a thick strip, doesn't matter. Actually, it's a very thin strip. So this is P, this is Q. And this region of integration is A, B, C, D. So earlier we would integrate for a function of single variable y dx. So dx will be on the, so we integrate over a line in along the x-axis. However, now we have to integrate over the area. So the region of integration, is ABCD. The the inner rectangular strip PQ represents integration over y while keeping x as constant. While keeping x as constant. So x doesn't change. So this PQ strip is actually a very, very thin strip. We have drawn thick, but it will just be like a very thin line. So while x is constant, we are integrating from q to p, that is y1 to y2. And then all such strips from x1 to x2. So this is the region of integration. And the function, the surface will be over the x-axis, sorry, xy plane, over the xy plane, that will be the surface. And this is the region of integration. Okay. So this is when y1 and y2 are functions of x. Now let us look at the second case where it will be reverse. Now when x1 and x2 are functions of y and y1 and y2 are constants, then first integrate with respect to x. First integrate f of x comma y with respect to x, keeping y constant or keeping y fixed. Then the resulting integral is integrated with respect to y. So this is how it is done. So we have, let us say, x1 is a function of y, x2 is a function of y, and y1 and y2 are functions of, are constants. You may have dy dx, but the way this is integrated is first we integrate with respect to x. Treating y as constant, and then substitute the limits of x. And then we integrate with respect to y. So this is the working rule. So This is the working rule. So now let's look at the graph again. The region. Now your y1 and y2 will be constant. So on the xy plane, this is say y1 to y2, and there will be a function that will change. X will be a function of y. So we can have a region like this. So the region of integration will be this closed figure. Again, A, B, C, D. This one is x1 is equal to f1 of y. X2 is equal to f2 of y. This will be the region of, this will be the area of integration. Now we are treating y as constant and integrating first with respect to x. So x is along the horizontal line. So we would be integrating along this strip. Okay. So the region of integration is the area A, B, C, D, and the inner rectangular strip PQ represents the region of integration over X while Y is kept constant. So Y is constant, Y value is not changing, but X value is changing. And it varies from this f of y1 to f of y2. So this is the region of integration. Now, what happens if both x1 and x2 and y1 and y2 are constant? Then this is easy, very, very easy one. This is the best, easiest of the integrals. When x1 and x2 are constants and y1 and y2 are also constants, then the region of integration is a rectangle. In this case, the order of integration does not matter. Okay. So what we get is this. In the previous cases, order of integration matters, but in this case, the order of integration does not matter. So this is y1, this is y2, this is x1, this is x2. So the region of integration so this is the region of integration. Now it does not matter how we integrate. We can take a vertical strip, that is, first we are integrating with respect to y, treating x as constant, and then we are integrating all such strips from x1 to x2, or we can integrate with respect to x first, so let's say this is pq, this is p dash q dash. So any way you can integrate. So this will be integral x1 to x2, y1 to y2, f of x comma y dy dx. This can be integrated like this. First integrate with respect to y, treating x constant. Then integrate with respect to x, the resulting integral. Or we can also integrate first with respect to x, and then we integrate with respect to y. So both will give the same result. Okay, both are going to give the same result. So let us do some problems based on this. Problems on multi-integrals. Double integrals, in fact, more precisely. First one, evaluate I is integral 0 to pi, integral 0 to x sine y dy dx. So how will this be? Now, see this. So this is a function of x. So y is a function of x, y1, y2. So y2 is a function of x, and x1, x2 are constants. So first we'll have to integrate with respect to y. So when we write the bracket, it means we are integrating first with respect to y, and then we'll integrate with respect to x. So when we are integrating with respect to y, integral of sine y is cos y minus cos y. Apply the limits from 0 to x dx. So now integral 0 to pi. Now apply the limits. We get minus of cos x minus of minus cos 0. Cos 0 is 1. So we end up getting 0 to pi 1 minus cos x dx. So this will be integral 0 to pi. This is x minus sine x when we integrate, and now apply the limits 0 to pi. So we'll get pi minus 0 minus of 0 minus 0. So answer is pi. Okay. Very simple. First we integrate with respect to y, and then we integrate with respect to x. So depends on the problem. Next, we'll do another problem. The second one, evaluate I is integral 1 to log 8 integral 0 to log y e power x plus y dx dy. So looking at the limits, one set of limits is constant, other set of limit, first limit is constant, second limit is a function of y. That means x is a function of y. So first we'll have to integrate with respect to x. So generally the inner integral, the differential is written first. For the outer integral, the differential is written later. So that we have to keep in mind. Now this is e power x into e power y dx. We are integrating with respect to x. So e power y is treated as constant, and e power x is e power x 0 to log y e power y dy. Now substituting the limits, e power log y is nothing but y. You get e power, I'll write in between steps. This is e power log y to the base e minus e power 0 times e power y dy. So this is 0 to log 8 y minus 1 times e power y dy. So now we can integrate by parts. 0 to log 8 y e power y dy minus 0 to log 8 e power y dy. So first one, integrating by parts, I late, exponential is the second function. So first function into integral of the second minus derivative of the first into integral of the second, the whole integral. This is e power y. Now this is y e power y minus e power y from 0 to log 8. minus e power y from 0 to log 8. Now let's substitute. So log 8 into log 8 minus 1 y minus 1 times e power y. E power log 8 minus substitute 0 minus 1 times e power 0. This is the first. Second one, this is e power log 8 minus e power 0. So here we get e power log 8 into log 8 minus 1. This is 1, so this is plus 1. Then minus e power log 8 plus 1. So we get e power log 8 into log 8 minus 1 minus 1, so minus 2 plus 2. Now e power log 8 is equal to 8. And the last step I'm changing. E power log 8 is 8. So 8 log 8 minus 8 to 16 plus 2. 1 second. Oh, I'm sorry. Made a mistake here. This is 0 to log y, but this is 1 to log 8. Mistake. One to log 8. So everything changes. One to log 8, 1 to log 8. So this is y will be 1. So this becomes 0. And this will be e power log 8 and e power 1. This is plus e. This is 0. So e power log 8 minus 2 is correct, plus e. So minus 16 plus e. 8 log 8 minus 16 plus e. Okay. So first, what did we do? We integrated with respect to x, substituted the limits, and the result that we got, we are integrating with respect to y, and again substituting the limits. Now next, can I go forward?
Yes, sir.
So next question, integral 0 to 1, 0 to 1, dx dy upon under root of 1 minus x square under root of 1 minus y square. Now both are from 0 to 1, so it doesn't make a difference how we integrate. We can integrate first with respect to x and then with respect to y, or so treating y constant, we'll first integrate with respect to x. So this integral 1 by root of 1 minus y square, and this is the integral of 1 upon root of 1 minus x square is sine inverse x from 0 to 1. This is sine inverse 1. This is pi by 2 minus sine inverse 0 is 0. So we get pi by 2. Now pi by 2 comes out, and then we have integral of 1 upon under root 1 minus y square with respect to y will be sine inverse y from 0 to 1. So pi by 2 sine inverse 1 minus sine inverse 0. So we'll get pi square by 4 as the answer. So this is the simplest types of integrals, where either y is a function of x, the first example, or x is the function of y, the x limits are the function of y, or both x and y limits are constant. Now look at this problem. Evaluate double integral of xy dx dy or dy dx over a, where this a is the region bounded by x-axis, comma, ordinates, ordinate x equal to 2a, and the curve x square is equal to 4ay. So now the region and the limits are not given in this problem. In the previous problems, the limits were given. Now here, the limits are not given, and we have to integrate finding the limits. So first of all, we have to draw the region of integration. So this is the xy plane. And now y square is equal to x square equal to 4ay will be a parabola like this. X square is equal to 4ay, assuming a constant. And the x-axis and the ordinate x equal to 2a. X equal to 2a will be this line. This is the region of integration. So we have x1 is equal to 0, and we have x2 as 2a. Now we this particular line is y1 is 0, and this is y2 is x square by 4a. Okay. So now we have to write the integral. So we need to evaluate I, which is integral, okay, xy dx. No, it's not. First, we have to integrate with respect to y. So, and then with respect to x. So y varies from 0 to x square upon 4a. Okay. This curve is y square equal x square equal to 4ay. So from there we wrote this as y is equal to x square upon 4a. Now from y1 to y2, and x varies from 0 to 2a. So this is the region of integral. So the integral looks like this. So when we integrate, first integrate with respect to y, keeping x constant. So y square upon 2. So this is integral 0 to 2a. X by 2 comes out. This is y cube upon 3 is the integral. No, sorry, it's already integrated. So y square upon 2. So 2 comes out, y square, substitute. We get x power 4 upon 16a square minus 0. So we get integral 0 to 2a x power 5 upon 32a square dx. So this will be 1 upon 32a square x power 6 by 6, 0 to 2a. So 1 by 32a square, 2 power 6 is 64, a power 6 minus 0 by 6. So 32 to 64 and by 3. So we get a power 4 by 3. This is the answer. So I integral is a power 4 upon 3. So this was a problem in which the limits of integrals were not specified, but we had to just find the limits of integration and solve for the integral. Okay, now another problem. This was problem 4. We'll do problem 5. All right, this is good. Evaluate double integral xy dx dy over a, where a is the positive quadrant of the circle x square plus y square is equal to a square. So this is a circle, and this is the x-axis. This is the y-axis. So we need to integrate over the positive quadrant of this circle. This is so. Now, because of symmetry, we can integrate either with respect to x or with respect to y. So this portion of the function, now this is y in terms of x. So y will be under root of a square minus x square. Y will be under root of a square minus x square. This is positive part. Below the x-axis, this will be y is minus root of a square minus x square. From this equation of circle, y we write as a square minus x square under root, plus or minus. The minus portion is this bottom part. The plus portion is this top part. So we can integrate along this strip. First, treating x as constant, integrate with respect to y. Okay. So we need to evaluate the integral. Integral x varies from 0 to a, but y varies from 0 to under root a square minus x square. And integral is x comma y dy. So dy dx. So this is what is the integral. Clear? So now what we do is, now let's start integrating 0 to a, treating x constant, integrating y. So we get integral 0 to a x times y square upon 2 from 0 to under root a square minus x square dx. Now 0 to a is x times half times, we get substitute under root of a square minus x square in place of y. This is y square, so under root goes away. We get a square minus x square minus 0. So taking half out, we get integral 0 to a square x minus x cube dx. This is half a square times x square by 2 minus x power 4 by 4, 0 to a. This a power 4 upon 2 minus a power 4 upon 4. We get a power 4 upon 4. So you get a power 4 upon 8. This is the answer. All right. Can I move forward?
Yes, sir.
So we did 3 problems straight, 2 problems where the area is not so clearly directly given, but it is given in terms of the verbal problem. So we did that. Now we'll do a double integral in polar coordinates. Okay, someone has asked this. No. Positive quadrant, will we not integrate x from minus a to a? Good question. No, because positive quadrant, it is both positive for x and positive for y. It is not just positive for x because this is the domain. Actual function xy is coming on the surface here along the z plane. So positive quadrant means within both x and y both are positive. So otherwise they would have said positive quadrants of x. Then it will be from minus a to. Anyway, in that case, the integral will be twice of this anyway, just a power 4 by 4 you will get. Now, next, double integral in polar coordinates. So question 6. Evaluate I is integral 0 to pi, integral 0 to a theta, r cube d theta dr. So r is given in terms of theta, and then theta is constant 0 to pi. So first we will have to integrate with respect to r. So I integral 0 to pi integral 0 to a theta r cube dr times d theta. So we get integral 0 to pi r power 4 by 4 0 to a theta d theta. So we get integral 0 to pi. This is a power 4 theta to the power 4 upon 4 minus 0. So this is a power 4 by 4 into theta to the power 5 upon 5, the integral from 0 to pi. So we get a power 4 pi raised to the power 5 over 5 into 4, 20. So this is the this is the definite integral. So double integral. So simple. First integrate with respect to r and then with respect to theta. We just need to be careful how we do that. Okay, let's do another one on this. Evaluate integral 0 to pi and integral 0 to a into 1 plus cos theta r cube into sine theta cos theta dr d theta. So again, the limits are in terms of theta. That means r is in terms of theta and theta varies from 0 to pi. So let us integrate that way. Integral 0 to pi, integral 0 to a to 1 plus cos theta r cube dr times sine theta cos theta d theta. So let's integrate this. Integral 0 to pi, this is r power 4 upon 4. 0 to a times 1 plus cos theta into sine theta cos theta d theta. So we get integral 0 to pi 1 upon 4 a power 4 1 plus cos theta whole power 4 minus 0 sine theta cos theta d theta. So now everything is in terms of cos theta. This power 4 1 plus cos theta whole power 4. So it's a binomial. Now instead of going that way, we can easily substitute cos theta as t, cos theta as t. Then we get minus sine theta d theta is dt. And look at the limits. Theta and t. When theta is 0, t is 1. When theta is pi, t is minus 1. So I will be integral 1 to minus 1 a power 4 by 4 into 1 plus t whole power 4 into t into sine theta d theta will be minus dt. So now let us simplify a power 4 upon 4 and then limits of integral changes from minus 1 to 1. If we remove this minus sign, then we have 1 plus 40 plus 60 square plus 40 cube plus t power 4 times t. How did I get? This is just the binomial expansion. 1, 4, 6, 4, 1 will be the binomial coefficients, and then just did the binomial expansion. Now this will become minus 1 to 1 t plus 4t square plus 6t cube plus 4t power 4 plus t power 5 dt. Now this is sum of odd terms and even terms. So we can split the odd and even parts. The odd parts t plus 6t cube plus t power 5 dt plus the even part 4t power 4t square plus 4t power 4. So this is an odd function and this is an even function. So because this is an odd function, from minus a to a of any function which is odd, the integral value will be 0. So we have simplified that. Now a power 4 upon 4, and this will be twice of integral 0 to 1 because it's an even function. 4t square plus 4t power 4.
Sir, I think there was a minus which was there above.
This one?
Minus dt.
So minus dt has gone. No? Minus dt becomes, because this is 1 to minus 1, it has become minus 1 to 1.
Oh, okay, sir.
Okay. So 4 comes out and 4 cancels with the bottom. You are having 2a power 4 into t cube plus 3 plus t power 5, t cube upon 3 plus t power 5 upon 5 from 0 to 1. So we get 2a power 4 into 1 upon 3 plus 1 upon 5. So we get 2a power 4 into 8 upon 15. So you get 16a power 4 upon 15. This is the answer. 16a power 4 upon 15. Okay. So these are again, so it is just a matter of simplification and carrying out. The fundamental concept is very, very simple. First, we integrate with respect to r, substitute the limits, and then integrate with respect to theta. And the rest of the problem is our skill of evaluating the integral. That's all. Now, next question. Now, let's say in polar coordinates, the area is not specified. So, evaluate integral r cube dr d theta over the area A included between the circles r equal to 2 sine theta and r equal to 4 sine theta. Now, the limits are not clear to us. Of course, we can, r is 2 sine theta to 4 sine theta. And then theta, where to where, we have to see that. So let us first draw the pole and the circle. This will be the initial line. This will be the line theta equal to theta equal to pi by 2. Theta equal to 0, theta equal to pi by 2. This is the initial line. This is the pole. Then this one will be theta equal to pi by 4. Sorry, theta equal to pi. And the last one, of course, I could have drawn just so this is the initial line, theta equal to 0. Initial line, theta equal to 0. This is the perpendicular line, theta equal to 90 or pi by 2. This is theta equal to pi. And the same line is theta equal to minus pi. This is theta equal to minus pi by 2. Now, when theta equal to 0, r is 0. Let us plot this one, 2 sine theta. When theta equal to pi by 2, r is equal to 2. Okay. And when theta equal to pi, r will be 0. And so we get now r value cannot be negative. Of course, it will be negative if I'll draw this circle. Yeah. Now, the second circle we get theta, if you vary from 0 to pi, you will get this. Double the distance. Okay. So this is r equal to 4 theta. So this is 4. This is 4 comma 0 is the 4 comma pi by 2 is the point. This is 2 comma pi by 2 is the point. 4 comma pi by 2 r theta. This is 2 comma pi by 2. Of course, when theta varies from minus pi to pi, then you get a circle below, but 2 sets of circle, take theta as 0 to pi, sufficient. Now, this is the area. Over this area, this function has to be integrated. So this is the region of integration. And we have to integrate r cube over this region of integration. So right here, we need to evaluate the integral I is integral r cube dr. R varies from 2 sine theta to 4 sine theta. So how do you integrate? Keep theta as constant. So look at this line. So yeah, theta is constant. And then this shaded region, this is r is equal to 2 sine theta to 4 sine theta. So we are integrating along the strips like this. And then we are changing theta from 0 to pi. So r cube dr, then theta varying from 0 to pi d theta. Okay. Now when we evaluate this integral 0 to pi, this is r power 4 upon 4 from 2 sine theta to 4 sine theta d theta. So we get integral 0 to pi 1 upon 4 into 4 power 4 sine power 4 theta minus 2 power 4 sine power 4 theta d theta. So this is 1 power 4 by 4 power 4 minus 2 power 4. Sine power 4 theta, if you take common, we get 4 power 4 minus 2 power 4. 0 to pi sine power 4 theta. How do we evaluate this? We'll have to use the Wallis expression. So 1 by 4, 4 power 4 is 16 into 16, 256 minus 16, that is 240. And this is twice of integral 0 to pi by 2 sine power 4 theta d theta. Applying the sixth property of definite integrals, f of a minus x is equal to f of x. Now, f of 2a minus x is equal to f of x. So then integral 0 to 2a f of x dx is twice of integral 0 to a f of x dx. So now, because Wallis will be valid only for limits 0 to pi by 2. So that we should never forget. Now Wallis formula, this will be 3 into 1 by 4 into 2 into pi by 2 because it's an even power. So 4, 6 are 24, so 60. Now 2 cancels, 4 15s, 4 15 times 60. So 15 threes 45 pi upon 2. So 22.5 pi. This is the answer. 22.5 pi. Okay. This is how we evaluate this integral. Next, for next half an hour, we are going to do something very important. We get many problems in the exam, the GATE exam, based on this concept, change of order. Change of order of integration in double integrals. Change of order of integration. We get several problems. So this will be based on our basis to do this. Change of order has to be based on geometry or geometrical considerations of the area of integration. So let's take examples. Question 1. So change the order of the integration. Change the order of integration in I is equal to integral 0 to 2a and integral x square by 4a to 3a minus x f of x comma y dy dx. So now first we are integrating with respect to y and then with respect to x. So no matter what the function is, now we need to change the order. So first thing to do is to have the idea of the shape of the area of integration. This is x, this is y. Now let's see. Now what is so this is we have the curves as the first curve y1 is this curve y is equal to x square by 4a. That means 4ay is equal to x square. It's a parabola. Now y2 is the curve y is equal to 3a minus x. So it is the line x plus y is equal to 3a. So first draw the parabola. Y square equal to x square equal to 4ay. So let's draw the parabola. This is the parabola. Now, this is x square equal to 4ay. So y is equal to x square upon 4a. And then we have the line. No, and then we have this line 3a minus x. So let's say this is a comma 0 is the focus, 2a, 3a. And then this is again 3a. So the line will be so this is the line. This is the point 3a comma 0, 0 comma 3a. So from the equation of the lines, this is in the intercept form of the line. So this is the line, this is the curve. So region bounded. Now, where do they intersect? This curve, where does it intersect? So if we equate, let's equate both of them. So point of intersection, we have to get x square by 4a is equal to 3a minus x. So we get x square plus 4ax minus 12a square equal to 0. So 6 into 2. So x square minus 2ax plus 6ax minus 12a square is equal to 0. So we get x into x minus 2a plus 6a into x minus 2a. So you get x plus 6a and x minus 2a equal to 0. So points of intersection, this curve cuts here. So x equal to minus 6a and here x equal to 2a. This is 2a comma 0. This is 3a comma 0. So there are 2 points of intersection again. X is equal to 2a and x is equal to minus 6a. Minus 6a, if we extend this line here, and we extend this parabola here, then this point of intersection is minus 6a, which is not required for us because the integral x is varying from 0 to 2a. In this region, we want from this parabola to this line. So this is the region of integration. So as of now, the strip that is taken is the vertical strip, keeping x constant, integrating y from y1 to y2. However, now we need to change the strip. We have to integrate with respect to we need to integrate with respect to x first, keeping y constant. Now, what happens? One portion is the x-axis, sorry, the y-axis, x equal to 0. This is x equal to 0, the y-axis. And now we have two curves. So when we take a strip, right now, this integral is taking the, I'll draw the strip anyway. Horizontal, vertical strip. PQ. Now we don't want this vertical strip. We want to take the horizontal strip. I will take a green line here. We want the horizontal strip. Now, horizontal strip, the curve is not constant. We have to write, see, y in terms of x we have written. Now we have to write x in terms of y. So this x will be root of 4ay, positive. This portion will be x is equal to minus root of 4ay. We don't need this. But this portion from the origin to this, in terms of y equal to, either in terms of x, it is y is equal to x square by 4a. In terms of y, it is x equal to under root 4a1. And this one, this is the equation of the line y is equal to 3a minus x, which is also x is equal to 3a minus 1. So now we need to integrate O, this point is A, this point is B. O, A, B, O, this region. So upon change of integral, okay, I'll write this statement so that it is understandable to you. I'll be sharing this. So limits of y are y is equal to x square by 4a to y is equal to 3a minus x. So we integrate using the vertical strip. Keeping x constant first, and then integrating with respect to x again. Now, if we have to integrate using horizontal strip, what happens? The region will have to be split into two parts. This, I will write this as D. O, A, D and D, A, B. So therefore now the integral will be, now look at this strip, keeping y constant, I integrate with respect to x. The first region, OAD, x varies from 0 to x equal to root 4ay. Now, second, integrating with respect to y varies from 0 to this point. The point of intersection is x is 2a. When x is equal to 2a, it's 4a square. So y will be equal to a. 2a comma a is the point of intersection. So y value will change from 0 to a. This is the first part. This is the first portion. OAD. Next, DAB is this triangular portion. So this will be integral x equal to 0 to x equal to 3a minus y dx. First integrating with respect to x, then with respect to y. Now y will vary from a to 3a. Because this is 0 to 3a. This is a to 3a. 0, d is 0 comma a. So from a to 3a. So although this integral was easy, single integral, but when we change the order of integration, it changes, it splits into two parts. So integral 0 to a, integral 0 to under root 4ay, f of xy dx dy, plus integral a to 3a, integral 0 to 3a minus y, f of xy dx dy. All right. So there's the change of order problems. These are very, very important problems. Extremely important. Let's do another one. The problems of this kind are very important, where when we reverse the order of integration, it splits into two integrals. It doesn't remain a single integral. Now we'll take a case where it remains a single integral. Let us see this. Change the order of integration for this integral, for integral minus a to a, integral a to root of a square minus y square, f of x comma y dx dy. So first step to do is to plot what this function is. Oh, this is, sorry, this is zero to minus a to a and 0 to root of a square minus y square. So x is varying from 0 to x is equal to under root of a square minus y square. So clearly this is x square plus y square equal to a square. So we are dealing with a circle. So we are dealing with a circle. So all right. So this is a circle. Now this portion x equal to 0 to x equal to a square minus y square. So x, this is x, this is y. X, this portion will be x is equal to under root of a square minus y square. And this portion is x is minus under root of a square minus y square. This is the negative x, this is the positive x. So x varies from 0 to under root a square minus y square, means x equal to under root of a 0 to a square minus y square, means we get this region, and y varies from minus a to a. So minus a to a. This is 0 comma a, and this is 0 comma minus a. So our region of integration is this. This is our region of integration. Okay. This is a region of integration. So now what have we done? So the integral now is a horizontal. The existing one is the horizontal strip. We are keeping y as constant. We are integrating with respect to x. This is the existing one. And what we need to change the order. Okay, understood, right? You know, x is varying from 0 to under root of a square minus y square. And now we need to integrate along the vertical strip. Okay, there's a vertical strip along which we need to integrate. RS, I'll say. The given order of integral is integration along the horizontal strip RS. Now, in changing the order, we need to integrate along the vertical strip PQ. Now, PQ means now y equal to some function of x to y equal to some function of x. So now here we have to write y is plus root of a square minus x square. This is x square plus y square equal to a square. So the bottom portion will be y is equal to minus root of a square minus x square. Okay. Y equal to minus root of a square plus x square to y is equal to a square plus x square. And now x will vary from this region 0 to a, 0 to a. So therefore the change of order of integration results in this integral I is equal to integral. Now y is minus under root of a square minus x square to under root of a square minus x square f of x comma y dy first and then dx. X varies from 0 to a. So x varies from 0 to a, but y varies from minus under root of a square minus x square to plus under root a square minus x square. Okay. So many such problems are there. I have a full list of integrals. I will share with you. Some of them we'll do them tomorrow. So tomorrow, one or two more problems on change of order of integrals, and then application of double integrals to finding volumes, areas and volumes of figures, and then triple integral. So these will be the topics for tomorrow. So I hope you have understood this part. It was simple, just that we have to have the grasp of geometry. That's all. And coordinate geometry of how to change the orders of the integral. All right, we'll stop for now.